So during the last two lectures, I have described various methods to do very precise spectroscopy on atoms. And I have tried to explain that in order to beat the Doppler effect, the most effective method was to stop atoms, to trap them in a very well-defined position, and to investigate, to manipulate these atoms with monochromatic laser beams. And I have shown that you can use lasers to cool the atoms, to bring them to the ground state of the harmonic potential in which they are trapped, and also to use another laser, or possibly the same laser, to detect the atoms by having them undergoing cycles between the ground state and an excited state at a very rapid rate, and by looking at the fluorescence of the atoms. And I have also described the shelving method, which consists in observing the moments when the atom leaves the ground state, for instance, because it interrupts the cycles of absorption and fluorescence. And I have described what is known as the quantum jump method to detect very weakly allowed transitions. I have described that for trapped ions and also trapped neutral atoms. In the case of neutral atoms, the light plays a double role. The light is used at the same time to cool and trap the atoms and also to investigate their energy levels. And they have shown that one can reach very, very high precision by using these techniques, which have been developed since, I would say, during the last 30 years, in the 1980s. So today, I would like to describe what can be done with these very precise spectroscopic methods to measure time itself with a very high precision. So I will talk about clocks, atomic clocks, microwave, and optical clocks. I would like to stress the fact that the progresses have been absolutely fantastic. If you look at the precision of clocks since the 17th century to the middle of the 20th century, the improvement has been maybe a factor of 4 orders of magnitude. The clocks, the pendulum clocks that Huygens had developed in the 17th century had an uncertainty of about 10 seconds per day. And they had shown to you that this 10 seconds per day uncertainty was good enough to make the first precise measurements in modern physics, in particular to evaluate the speed of light itself. So it was about 10 minus 4, it's about 10 seconds per day. In the middle of the 20th century, before atomic clocks, the uncertainty was about 10 minus 8, about 1 millisecond per day with quartz clocks. And so it was a progress of 4 orders of magnitudes in 3 or 4 centuries. But since 1950s, because of the development of atomic clocks and optical clocks, we have now an uncertainty of 10 minus 19, which is something like 11 orders of magnitude better than the clocks at about 70 years ago. So there have been a fantastic progress, and this progress has made possible a lot of experiments which we could not dream about, let's say, a few decades ago, and I would like to talk about that in this lecture. So first of all, I will remind you what we have said about hydrogen spectroscopy. Hydrogen is, of course, the simplest atoms. The energy levels of hydrogen are known theoretically with a very high precision. So doing experiments on hydrogen is a test bench to demonstrate or to illustrate the precision of laser spectroscopy. Then I will remind you, make again a brief history of time measurements from pendulums to atomic clocks. I will talk about the frequency comb revolution. I already alluded to frequency combs about 2 or 3 lectures ago when I talked about mode blocking and the ability to generate intense and very short light pulses to do attosecond spectroscopy. So the femtosecond laser comb can be used to achieve very short pulses, but it also can be used to achieve extreme precision, as I will be discussing today. And then I will describe two kinds of modern atomic optical clocks, the optical clocks which are made with trapped ions, and the optical clocks which are made with neutral atoms. And the neutral atoms clock that I will be discussing at the end of the lecture have achieved this uncertainty of 1 part in 10 to the 19, and we'll talk about these achievements. So on this slide, I remind you of the spectrum of the hydrogen atom. So it's just a 1 electron atom. You see the ground state, n equal 1, and then you have the excited state with n equal 2, 3, and so on. And you see the transition which links the ground state to the excited state from what is known as the Lyman series. The transition which starts from n equal 2 forms the Balmer series, and the Paschen series starting from n equals 3. So this is a spectrum as it is described by the non-relativistic Schrödinger-Bohr-Schrödinger theory, non-relativistic theory. Then if you add relativity, you have to solve Dirac's equation, which I also discussed in one of the early lectures. And in this case, you see that you have to take into account not only the principal quantum number n, but also the angular momentum, L, which takes the value 0, 1, 2, up to n minus 1. And traditionally, n equals 0 are called S states, L equal 1 are called P states. And you see, for example, in the n equal 2 manifold, you have S and P states. And the index, which is here, is the total angular momentum, which is the sum of the orbital momentum and the spin momentum. So you see S, the S state have a total angular momentum equal to 1/2 because the orbital momentum is 0. But when the orbital momentum is 1, J, the total momentum, can be 1/3 or 3/3. And the separation between the two is called the fine structure. It's about 10 gigahertz. This fine structure is due to the interaction of the orbital magnetic moment with the spin magnetic moment. And if they are oriented in the same direction, the energy is different from it is when they are oriented in the opposite direction. So this is the reason of this splitting here, which is about 10 gigahertz. So, and according to Dirac, the states with the same total angular momentum, 2s1/2 and 2p1/2, are exactly degenerate. Now, the last thing to take into account are the vacuum quantum fluctuations. And I talked already about the lamp shift. When you take this quantum fluctuation into account, the lamp shift lifts the degeneracy between S1/2 and P1/2. This is about 1 gigahertz. This is the lamp shift which was measured in the microwave domain by Lamb in the 1940s. And the ground state is also shifted by a larger amount, 8 times larger, about 8 gigahertz. But it is very difficult. It was at that time very difficult to measure the lamp shift of the ground state because you had to be able to measure a difference of 8 gigahertz on a huge optical frequency. So what has been achieved with laser spectroscopy on this spectrum? I show you here, I remind you here the first experiment which was performed by Ted Hench. It was called laser saturation spectroscopy. The scheme is to excite the hydrogen with 2 counter-propagating beams, one intense beam in one direction and one weak probe beam in the opposite direction. And by doing that, you can use saturation effects to suppress the Doppler effect. I remind you that if you have 2 beams propagating in opposite direction, and if the atom is moving, then the 2 lasers interact with different classes of atoms because of the Doppler effect. And only if the lasers are exactly on resonance do they interact with the same class of atoms which propagate perpendicularly to the laser beam. So doing saturation spectroscopy is to select among all the atoms in the sample, the atoms which make a kind of sheet of atoms with velocities perpendicular to the laser beam. And these atoms give a signal which is very narrow, much narrower than the Doppler width. So you see here, this is a Balmer line. it's a red transition. It's a line 2n equal 2 to n equals 3. Before the lasers, one could barely see the splitting, the 10 gigahertz splitting of the fine structure, but all the hyperfine, all the splittings due to inside the S and P state was completely hidden in this broad structure. And you see when Hench performed the first saturation spectroscopy experiment, he was able to observe for the first time the lamp shift, this difference of about 1 gigahertz between this peak and that peak. So this was the first demonstration of high resolution spectroscopy with lasers. But of course, it was still rather crude because the lasers were pulsed lasers, and the width of the line width of the lasers themselves was of the order of 1 gigahertz, of the order of the lamp shift. We will see at the end of this lecture that now we can have laser beams which have a line width of a few millihertz, that is billions of times narrower than the lasers which were used in these early experiments. Now, if you want to observe the lamp shift of the ground state, what you have to do is to do spectroscopy on a transition from n equal 1 to n equal 2. This is very fine, the UV. And what I have discussed in this context is to do 2 photon spectroscopy. That is, instead of trying to connect the ground state to the n equal 2 states with just one very far UV photon, you can use 2 photons which fall in the near UV around 2,400 angstrom. And if you absorb one photon going in one direction and another one going in the opposite direction, you suppress the Doppler effect and you suppress the recoil. And so you have very narrow lines. You see here the line obtained, which is about 500 hertz wide. And I show you here the experimental setup. It's a beam of hydrogen. Hydrogen molecules are dissociated in its discharge, and the molecules diffuse in this direction. Here you have a cold finger, which is cooled by a cryostat at helium temperature, because you want to have cold hydrogen, because you suppress the first order Doppler effect, but you still have the second order Doppler effect, which is a relativistic effect, which is the fact that in the frame of the atoms, the time evolves more slowly due to special relativity. It's a V square of a C square effect, but with the precision of this experiment, it can be observed. So what Hench did was to use cold hydrogen, which moves rather slowly at a few hundred meters per second. Hydrogen is very light, so it has a very high velocity at room temperature. So at low temperatures, the velocity was 100 or 200 meters per second. The atoms were moving in vacuum. And here you had a cavity made of these 2 mirrors, and the light, this laser light was, which was at this frequency, was going back and forth. And so the atoms were seeing 2 counter-propagating beams. What happened, the atoms were excited by this light, and when they reached this point here, an electric field was applied, which mixed the 2s state with 2p state. The 2s state has a very long lifetime, but as soon as you mix it to the 2p state decays to the ground state, you get a Lyman alpha photon, and this photon was the signal that the atom had been excited by the laser. So as you scan the laser, you see a resonance when the transition condition is fulfilled, and you see the transition here with the emission of Lyman alpha photons. The last trick here was to have a wheel which was shopping periodically the atomic beam. What was the purpose of this shopping? The idea was the following. If you shop the atomic beam, you get pulses of atoms going through. And if you delay conveniently this wheel with the detection that you apply here, you can select slow atoms. If the atoms are going fast, they will go past the detector and will be lost. But if you are conveniently synchronizing this with the detection here, with the pulse of electric field you applied here, you can select very slow atoms. Of course, you have all kinds of velocities in the atomic beam, but in the tail of the velocity distribution, you have slow atoms. And of course, for slow atoms, the second order Doppler effect is smaller. So by doing very careful experiment of this kind, Haroche was able to minimize the second order Doppler effect and to get narrow lines, which allowed him to do very precise spectroscopy on hydrogen. And I summarize all these results on this slide, which I think I've already shown to you also. You see here the progress of spectroscopy of hydrogen from 1920 to now. From 1920s to the 1950s, the progress was rather slow because the Doppler effect could not be overcome by classical techniques. But as soon as lasers appeared, you see the slope change suddenly. This red point corresponds to laser spectroscopy, the kind of experiment I just described. And then you had another increase in the slope when it became possible to measure directly the optical frequencies. And this is what I will be discussing in the second part of the talk. And you see now the precision is about 1 part in 10 to the 15, 10 to the 14, 10 to the 15. So what kind, just to show the precision which has been reached here, I give you a few figures. This is the frequency of the 1s to s transition. It's about 2.4, 10 to the 15 hertz. And you see that the delta nu over nu is 4 times 10 minus 15. So a very, very good precision in the measurement of this frequency in hydrogen. The second quantity here is the Rydberg constant. The Rydberg constant is alpha square mc squared over 2. You see the precision is not as good. It's only 10 minus 12. The reason is that in the Rydberg constant, when you connect the frequency to the Rydberg constant, you have to know very well the electron mass and the proton mass, because mass which appears here is a reduced mass. You have to take into account that, in fact, when the electron is going around, the nucleus recoils, and you have an effective mass which is slightly different from the mass you would have if the nucleus had an infinite mass. And so the reduced mass of the electron is not known better than 10 minus 12, and that's why you reduce the precision of the Rydberg measurement. It's less precise than delta nu over nu. Another figure which is very interesting is the ground state lamp shift, 8 point something gigahertz, which is done with 6 significant figures. It's a very small difference over the big optical frequency, but you still see that it's known with a very high precision, and all these figures up to this point agree with the theory of quantum electrodynamics. So it's a great success of these theories. What I want now to stress is the fact that in order to reach this high precision and to give this figure, it's not sufficient to have good lasers. You need to have good lasers, but you need also to be able to count very, very fast frequencies in the 10, 14, 10 to the 15 hertz. And this is what I will discuss later. So this being said, I will recall you very briefly the various stages of improvement over the measurement of time. You see here the principle of the tower clocks in the churches in the 14th or 15th century. The time was measured by this kind of clocks. You had an horizontal bar, it's called a foliot, which was going back and forth. It was suspended to a string, and the torsion of the string made it oscillate with a period which was a few seconds. And you had an escape mechanism, this dented wheel, which was counting the number of oscillations and making a hand move on a dial. So it was kind of a clock, but very imprecise. It had a precision of about 1/4 of an hour per day, which is about 10 minus 2. So that was the state of the art at these early times. And what I will stress when I will show you and remind you of the different stages is that the improvement in precision is directly proportional to the period. if you want to measure time with precision, you have to increase the period of the oscillation that you are measuring. So here it was a period of a few seconds. The first improvement was made by Huygens in the 17th century when he developed the pendulum clock. The pendulum clock is the same principle, but now it's a pendulum going back and forth with a period of about 2 seconds. And you have also an escape mechanism, and you have a weight which is going down in the gravitational field to provide energy which is compensating for the losses due to friction of the pendulum. So it's the kind of clock that we still have today. And the precision was 10⁻⁴, let's say 10 seconds per day. And I showed you in the first lecture that it was hardly sufficient to see the effect of finite velocity of light when looking at the satellite of Jupiter. And this was the first really quantitative measurement using a clock in the history of physics. But this kind of clock was, in fact, one of the first uses which were considered for clocks was the measurement of longitudes. It was a time when the first navigation and exploration of the world had started. And of course, the navigators understood that if they could carry a clock which kept the time of the harbor that they were leaving, by comparing the time of this clock with the local time, observed by observing the sun or the stars, they would know the time, the jet lag, not the jet lag, but the time difference between the 2 points, and they would have the longitude. But the problem with the Huygens pendulum clock is that it cannot keep this precision on a boat which is moving back and forth with all the accelerations you have there. So it was impossible to keep the precision of 10 seconds per day with this kind of clock. So people have tried from that time on to develop more compact clocks, which are the kind of mechanical clocks which we have been using for centuries, instead of the motion of a pendulum, which has a period of about 1 second. It's the oscillation of a spiral spring, which oscillate, let's say, at about 100 hertz, something like that. And so the precision is improved by this factor of 100. And we have now a relative uncertainty of 10⁻⁶, which is about 1 second per month. But it took almost all the 18th century for clockmakers to be able to build all the mechanical hardware which was required to make this kind of clocks. In fact, the British Admiralty had declared a kind of given a prize to the clockmaker would be able to build this clock. And Harrison was a clockmaker in England, developed the first marine chronometer, which had a precision of about 1 second per month. 1 month was about the time it took to cross the oceans. And so it was possible to keep the time of Greenwich or the time of London within precision of about 1 second over a month, which was very good to measure the longitude. Then there was about 1 century, another century, maybe 150 years going without, and you see, so the principle is to have a periodic motion and an escape mechanism which is counting the periods, which is how these clocks work. Now, the next progress was made at the end of the 19th century, beginning of the 20th century, by discovery of the Piezoelectric Effect by the Curie brothers in the 1880s. So I remind you what the Piezoelectric Effect is. If you have a crystal of quartz, for instance, and if you press on the side of a crystal, charges develop on the side, positive charge on one side, negative charge on the other. Now, if you're an acoustic wave, a periodic wave which makes periodic compressions, the charges are oscillating, positive and negative charges. And if you connect them with a wire, you get an alternative current, which oscillate at the frequency of the mechanical oscillation. So this piezoelectric effect is coupling mechanical vibrations of the quartz with electrical currents. And electrical currents are things that you can measure at relatively low frequencies. You can build an electronic circuit which counts the frequencies. Here, the frequencies are about, let's say, a few tens of kilohertz. It's another improvement of about a factor of 10 or 100 over the mechanical clock. And in this way, one was able to build clocks which gave a precision of about 10⁻8 to 10⁻9, which is about down to about 1 millisecond per day. So this was the state of the art up to the middle of the 1950s or so. Here, in fact, the discovery of the piezoelectric effect was made in 1880, but the first quartz clocks were developed something like 30 or 40 years later in the 1920s. Why? Because you had to be able to build electronic circuits which were able to amplify the small signals and count the frequencies. And for that, you need lamps, triode lamps, which were developed for radio communications, like work of Marconi, for instance. And you see the progress, tremendous progress was made during the First World War for development of this kind of electronics, which was then coupled to the quartz oscillators. And this is an example of the long time it takes between fundamental discoveries, here the piezoelectric effect, and applications to build something useful, which is a quartz clock. So the first quartz clocks were developed in the 1920s. Then they improved until the 1950s. 1 millisecond per day is interesting because this is a precision, the uncertainty in the rotation of the Earth itself. Before that, the time standard was linked to the revolution of the Earth on itself, 24 hours or 86,400 seconds. And when you get this kind of precision, 1 millisecond per day, you start to see that the Earth is slowing down very slowly due to friction, due to the influence of the moon and things like that. And so sometimes you have to add a second, a leap second. And this was a hint of this effect was already perceived by comparing the regularity of the motion of the Earth with the most precise quartz clocks of that time. So this was about the state of the art before atomic clocks. And you see the precision was limited to about 1 millisecond per day, but there was another imperfection, is the fact that all these clocks up to that time were man-made. In fact, for example, the quartz was cut, was machined, and if you change the size of the cut of the quartz, it will oscillate at a different frequency. The pendulum also depends, the frequency of the pendulum or the frequency of the spring depend upon the way it is built. So two clocks or two pendulums do not oscillate at the same rate. You can lock one to the other, you can compare the frequencies, and of course, the fact that the time is an objective quantity comes from the fact that the ratio between two clocks remains all the same. But it's not an absolute calibration, and with atoms, it will become different. And of course, another problem with mechanical or man-made clocks is that they wear out. As they work, they lose their properties. The different parts become old and do not work anymore well, whereas an atom is always the same. The cesium atom or rubidium atom in the universe are all the same, and they don't wear out. They always work in the same way. So I come now to atomic clocks. The idea of atomic clocks was given by Rabi back in the 1940s. I remind you that Rabi was the man who invented the molecular atomic beam and molecular beam resonance, magnetic resonance experiments. And he understood back in 1940s that these magnetic moments which are rotating in atoms could be used as timekeepers. You see here the cesium clock is based on the transition. In the ground state of cesium, you have a level with total angular momentum equal to 3 and another angular momentum equal to 4. Here, the angular momentum is the combination of the electron spin with a nuclear spin. And if you want a classical interpretation, what happens is that magnetic moment of the electron is rotating around the magnetic field produced by the nucleus. And this rotation occurs at a frequency which is, of course, proportional to the magnetic field seen by the electron. And the frequency is very stable. In the case of cesium, it's about 9.1 gigahertz. So if you follow the rules that I gave before, 10 gigahertz is about 1 million times larger than the quartz clocks. So the precision is increased by a factor of 1 million. Instead of 10⁻⁸, you get now 10⁻14, which is about 1 nanosecond per day. So now we have made a huge jump in precision. How is the measurement of this frequency made? The technique is something that I have already discussed. You see here, first of all, I show you here the energy diagram of the ground state of cesium as a function of the magnetic field. This is the F equals 3 state. You have 7. It is decomposed into 7 substate, and the F equals 4 state is split into 9 components. And in magnetic fields, they evolve in this way. So you see that you have 2 families of states. You have the states whose energy increases with the magnetic field. When the atom is in this state, it will like to go down. So it's called a low field seeker. Whereas if you are in the other state here, you see that the energy decreases with increasing field. So the atoms will like to roll down, and they are high field seekers. This is important because if you put a gradient of magnetic field, like a Stern-Gerlach experiment, the states, the upper state and the lower state will go in opposite directions in the gradient. So the gradient of field would be a kind of filter which will separate the high field seeker from the low field seeker. Moreover, there is one state, the state which have m equals 0, are states which in a given magnetic field, which is a magic field, do not depend on the magnetic field to first order, which means that if you set the magnetic field to this value, the frequency m equals 0 to m equals 0 will be practically independent of small variation of the magnetic field. So it's a factor of stability for the clock. So once you have done that, how do you measure the transition? You do, of course, magnetic resonance. And you do magnetic resonance according to the method that Ramsey had invented. That is that you expose your atoms to 2 pulses, 2 time separated pulses of microwave here and there. So you have here the atomic beam going horizontally, a first Stern-Gerlach which selects the low field seekers here, and then another Stern-Gerlach which will select the levels going up. So if you get a signal, it means that the microwave has made a transition between the low and the high field seekers. And of course, we know I describe the method of Ramsey spectroscopy. You see that you have fringes. If you scan the frequency of the microwave, the signal will go up and down, and the fringes will be narrower and narrower when the time between the 2 pulses increases. So you have an interest to have, of course, slow atoms. And of course, if you have slow atoms, it means that you interrogate them over a longer time. And according to the Heisenberg enthalpy relations, you get more and more precision. So it's why it's useful to have very narrow Ramsey fringes. And I show you on the next slide a general general procedure here. This is an anatomic clock. You have here the oven which produces cesium. The cesium beam is evaporated in vacuum. Here you have the 2 microwave zones which are fed by a waveguide here. And these are the magnetic gradients, Stern-Gerlach here and here. And the atoms which go through fall on a wire, hot wire. And when the atom comes on these wires, they get ionized and you get an electric current. And the intensity of the electric current tell you how many atoms have reached the wire. And when you scan the frequency of this microwave zone, you get fringes. These are the central fringes. Of course, if you go away from the central fringes, the intensity will decrease. The important point here is the interfringe distance is inversely proportional to the time it takes for the atom to go from one zone to the other, which I call T Ramsey. So from that, we can evaluate the precision or the uncertainty of this kind of clock. Delta nu over nu is delta fringe, the difference of frequency here, divided by the frequency of the cesium clock. And of course, you can divide the fringe. You can find where you are between two fringes with a factor which is called the signal-to-noise ratio. That is, the more atoms you detect, the narrower is this signal, and you get a very high precision. So you have to divide delta nu over nu by the signal-to-noise, S over N, and you get this result here. And we know everything here. Nu cesium is 9.2 gigahertz. The Ramsey time between the two zones is about is a delay of about 0.1 hundredths of a second. The time it takes to fly for an atom to fly from between the two zones, which are a few tens of centimeters away. And what is the signal-to-noise? The signal-to-noise is easy to understand. You know, when you detect an atom, according to quantum physics, you can only predict the probability for the atom to be in one state or the other. So you have, of course, around the mean value, you have a dispersion. And this dispersion is inversely proportional to the square root of the number of atoms. It's a general rule, statistical rule. The more atom you put, the narrower is the average curve. That is, more precise is the measurement. And you increase the precision by having more and more atoms detected. And you detect more and more atoms by averaging over longer and longer times for each frequency. And so the signal-to-noise increases as the square root of the time of measurement on each point. So it's what is written here. You see, the signal-to-noise is about 3,000 over 1 second. If you wait only if you average the millions of atoms that you see during 1 second, you get a signal-to-noise of 3,000, which means that the thickness of this curve, the thickness of the line here is about 1,000th of the distance between two maxima. And you see that the general rule, which would be applied in all what I will say now, is that you increase the precision as the square root of the time. If you wait 100 seconds, you will get 10 more precise results. If you wait 10,000 seconds, that is, let's say, a few hours, you increase the precision by a factor 100. And of course, this does not work up to infinity. In fact, practically what happens is that after 1 day or 2 days, that is after about 100,000 seconds, then you get long time drifts. The fact that it's impossible to keep all the parameters fixed for a long time. And so the precision increases, reaches a minimum, and then decreases again. So I will give you two figures here. The precision with 1 second of averaging, which is the result shown here. It's 3 × 10⁻12 per second. And then the result after about 100,000 seconds, after 1 day, which is about 100 times better, which is the absolute precision when you average over a reasonable time of 1 day. And you see indeed here that after 1 day, you get about 10⁻14 seconds per day. 10⁻14 per day, which is about 10⁻9 seconds. And this is again what I said to you before. This kind of clocks make an improvement of 6 orders of magnitude over the quartz clocks of the time. So what people have started to do then is to lock the microwave to be at the center of this line, and then to compare the microwave to a harmonic of a quartz. So you take a quartz, which is at a much lower frequency, and you compare this frequency to a harmonic of the quartz, and it means that the quartz is a divider of this atomic frequency, and these quarks which divide the atomic frequency are the new standard of time. In fact, in the 1970s, the second has been defined as the 9.2 time the period of the cesium transition between the two hyperfine states, and all the clocks are locked. The official time is given by quartz clocks, which are locked, permanently compared to this cesium standard. Then, in the 1990s, the lasers came into play. And the first use of the lasers has been to transform, still have a microwave clock, but to use laser manipulation to replace the Stern-Gerlach, and also to use slow atoms instead of thermal atoms. If you decrease the velocity of the atoms by a factor of 100, you increase the sensitivity of the precision, the uncertainty of the clock by this factor of 100. So this has been the birth of what is called the fountain clock. The explanation is simple. What you do here, first of all, you prepare rubidium or cesium atoms in a MOT. I remind you that a MOT is made of 6 counter-propagating beams in all directions, which slow the atoms in all directions. You add a gradient magnetic field, and you have a trap of cold atoms. So you have a trap of cold atoms here, and then at some time, t equals 0, you just increase the intensity of the laser going from down to up. So that is, you give a push of the atoms up. So the atoms leave the MOT, go up, and then they fall down in the gravitational field of the Earth. So it makes a fountain. And the time it takes for the atoms to go up and down is about a second. If you throw a ball up, the time it takes to go up and down is just maybe half a second. And on the way up and on the way down, the atoms cross this ring on which it's an electrode which apply a microwave. So the Ramsey pulse is now the same zone, which is crossed twice by the atoms going up and down. And how do you prepare? You prepare the atoms by optical pumping in F equals 3. You let the atom go up and down, they undergo a transition from 3 to 4. And then when they fall down, they cross this detection beam. And if they are in the F equals 4 state, this laser is adjusted to absorb and to fluoresce. And so the fluorescence of the atom which fall on this, in this beam is a signal. So you see, it's no longer a hot wire, it's really an optical signal. So lasers are used to cool the atoms, to get slow atoms, and they are also used to detect the atoms which have undergone the transition, but it's still a microwave transition. So how do you win when you do that? You see now the Ramsey fringes, they are much, much narrower. They're about 100 times narrower because the atoms have a velocity which is 100 times smaller. And you gain this factor of 100. Now, the uncertainty is about 5 times 10 minus 14 per square root of a second. And so after 1 day, you get 10 minus 16, which is now 10 picoseconds per day, 10 minus 11 seconds per day. This is, if you want to have another figure which will tell you maybe more what's give a better feeling. 10 minus 16 is about 1 second for several million years. This means that you have 2 clocks like that, which you synchronize. They will keep the time within better than a second over millions of years. So that's a huge improvement. Now, what can you do? What is the ultimate thing you can do with a microwave clock? Instead, you can try to increase more the time between the 2 Ramsey pulses. Of course, one way would be to push them up and to have them going up and down over a longer time, but it becomes very, very difficult, except if you are in space. And so the project, which I show the next slide, is called the Pharaoh Clock Project. It's a French project by the French Paris Observatory. They have built a clock which will be, which is shown here. So it's a cesium clock with very slow atoms in 0 gravitational field. If they are in the satellite or in the ISS station, the atoms can be, they don't fall, of course, and they can go at a velocity of about a few centimeters per second from one zone to the other. And then you expect to win another factor of 10 on the precision, and you will reach 10⁻17 per day. Now this project is ready, the clock is ready, but apparently they have problems to get it on the ISS, and for many years it has been delayed. The hope is that it will be sent in one of the future missions of the ISS. This kind of clock with this precision will be able to do relativity tests, special and general relativity tests, and I will talk about this test a little bit later. So now we have come to the limit of what can be done with microwaves. If you still want to improve the precision, of course, the next step is to have an oscillator which is even faster than this 9.2 gigahertz. And of course, you will have a much faster oscillator if you go to an optical transition. If you lock your clock to a transition in the optical domain and with a very narrow band laser, and if you lock the frequency of this laser to the atomic transition. But of course, this will be useful only if you can measure the frequency of this transition. There are two ways to look at that. One way is to measure the transition with respect to the microwave clock, which is still the standard of time. And the other way is to say, okay, I will get rid completely of the microwave standard, and I will use this optical transition as a new definition of the second. But of course, if I want to do that, I need to have an escape mechanism which will allow me to divide this very high frequency by a very precise number, because what we measure with on a dial or with a quartz clock is something, it's not 10 to the 15 hertz. You measure a subdivision, a divider of this high frequency. So the question is, can we build dividers of optical frequencies and use these dividers as new clocks? I gave you, in one of the earlier lectures, I showed you that there was a way to measure some high frequencies, but it's a very cumbersome and very difficult experiment. What you do is that you start with a microwave standard or with a quartz, and you multiply the frequency, and you start to compare the frequencies of infrared or far infrared lasers with a multiple of the quartz. Then you take a harmonic of the far infrared laser to build a higher frequency laser. Here you see, for example, CO2 laser, long tube of red lasers, and you beat and you compare higher and higher frequencies. You make what is called a frequency chain, which links microwaves to optical transition by multiplying the frequency by a factor of 0, 10 to the 4, 10 to the 5. So these are kind of tour de force experiments, and one of them in 1972 was the experiment which gave the final value for the velocity of light, and I described you that experiment. But of course, you cannot replicate this kind of frequency chains everywhere, and it was not convenient at all to build a clock until, again, Ted Hench and John Hall. John Hall is the guy who made this measurement. Ted Hench, we talked about him already, and both they independently invented the frequency comb, which is a device which made all this possible. So I will spend now the rest of the lecture talking about the frequency comb. I think I already gave you a first description of frequency combs when I talked about ultra short light pulses. I remind you that what we discuss is the fact that when a laser can oscillate on many, many modes. In fact, the resonant frequency in a cavity requires that you have an integer number of half wavelengths between the mirrors. So if you increase this integer number by 1 unit, you increase the frequency by a very small amount, which is C/2L. And so you see that, in fact, a laser can oscillate on modes which are separated in frequency by a fixed amount. And if the medium has a wide amplifying range, if it's a broadband amplifying medium, you can have hundreds or thousands of modes which are almost equally spaced, which oscillate at the same time. So this is a multi-mode laser. But usually what happens is that the different modes oscillate with random phases. So they don't interfere, they just give you a kind of steady state output because the modes are not, do not have a phase relationship. But if you can manage to have a phase relationship between the modes, what does it mean? It means that at a given time, all the modes are up. So they interfere and give a huge peak of intensity. But if time goes away from this time, of course, some modes go faster than others. So this condition goes away, and so the light intensity drops. And then you have to wait until the next coincidence happens again. And this is a property of Fourier transform. What you find when you do that is that, in fact, the time which separates two maxima is inversely proportional to, is just 1 over the frequency between the modes. And the width of each pulse is just proportional, is inversely proportional to the number of modes which interfere. If you have a large number of modes, this condition will be satisfied over a very short time. So this is what is indicated here. You see here, if you have a lot of modes like that, they interfere positively at times separated by 1 over the frequency difference Fr. And if you look, if you make a close-up to look at what happens in each pulse, you see here, I have made the close-up here. The width of each pulse is Tr over n. And what is each pulse? You have an envelope, which is shown here. And inside the envelope, you have, of course, the fast oscillation of the electromagnetic field. So you separate the envelope. You have two important ingredients here, the envelope, and inside the envelope, the carrier. And what is the carrier? It's an oscillation which is at the average frequency, which is here at the center of this distribution, the frequencies that you see here. And what happens from pulse to pulse is that usually you have a drift. You see that the oscillation inside the envelope does not, is shifting from one pulse to the next. And this is due to the fact that the phase velocity, which is the velocity at which the maxima evolve in time, is different from the group velocity, which is the velocity of the maximum of the pulse. And so this mismatch between the phase and the group velocity makes the structure inside each pulse unstable, oscillating with time. What I will show you on the next slide is rather simple. You see that the frequency of each of these peaks here, Fp, is a multiple of Fr, but there is no reason why it's an exact multiple. You have an offset. The frequency is a multiple of Fr plus an offset F0. And this is this offset, the existence of this offset, which explains the drift inside the pulse. And if you want to have a precise control of this multi-mode laser, you have to be able to measure separately Fr and F0. And this is the kind of thing which has to be done to be able to characterize properly this laser. And this is called a frequency comb for obvious reason. It's a comb of frequencies in which the difference between two frequencies is well known and the offset is well known. So what are the questions that we have to answer? Of course, the first question, what is the mechanism for mode blocking? Why? What we have to do to get the mode laser locked? How can this mode blocking be extended to an optical octave? It means that you have, in fact, what I will show you is that you have this kind of combs which extend from an optical frequency nu to 2 nu. So you have a huge range, and we need to have this factor of 2, this octave, as we will see in a moment, to be able to do precise experiments. On which parameters of the laser do Fr and F0 depend? What are the parameters? What are the knobs you can tune if you want to fix Fr and F0 to a given value? How do you calibrate these quantities? How can you use this frequency comb for spectroscopy? And how can you use it as an escape mechanism in an optical clock? And then, of course, what can you do with all this? So these are the questions I will try to answer. Here, on this slide, this slide is another way to look at the same problem. You see here, a cavity, if you have 1 mode, 2 modes, 3 modes, 4 modes, 5 modes beating together, you see as you increase the number of modes which beats, you form shorter and shorter pulses. If one of the mirrors is slightly transparent, each time the light is going back and forth, there's a small fraction of the light which escapes in the form of a pulse going out. And this is just translating what I already said. In fact, what you have when the laser is mode locked, what you get is a pulse, a very sharp pulse of light going back and forth between the mirrors. And each time this pulse reaches the output mirror, a small fraction is going out. So you get a train of pulses whose period is 1/fr, and whose width is TR/n. So these are exactly the quantities that I already discussed, and this is a general property of Fourier transform. And again, at the bottom of the slide, I again show that in general, you will have a kind of drift from pulse to pulse between the envelope and the carrier. And in order to show you that on this slide, I have chosen, and I will not enter into the details, but I have chosen a very simple example to allow for analytical calculation. I have assumed that the comb is made by F0, which is the offset, and then you add a frequency FR, 0 FR, 1 FR, 2 FR, and so on. And I assume that all the modes have the same amplitude. So it's a kind of square spectrum, a kind of in which I have n mode going from n equals 0 to n. And so in this case, the calculation is very simple. You just have to sum over a geometric series. Each time you had a new mode, you have to multiply by e to the 2i pi FRT. So it's just the term of a geometric series. And you know how to sum a geometric series. You get this expression here, and you get sine n pi FRT over sine pi FRT. This sine nx over x is a well-known function. It's a function which takes maxima each time the denominator cancels. You get 0 over 0, and you get a factor n. You get n. So you see that at this time, the amplitude is n times larger. And you see immediately that the condition for sine pi FRT to be equal to 0 is just the condition to be at the maximum, to be at t equal to FR equal t equal k over FR, which is TR. So you get exactly what we have seen already. And you see also from this expression that the phase shift, the phase drift delta pi is just 2 pi F0 over FR. So you see that you will have a phase drift unless F0 is a multiple of FR. And of course, if F0 is a multiple of FR, it means that all the frequency of the comb are multiple, all are multiple of a given number. So you have the offset does not matter anymore. So you have this condition, and you see what are the parameters on which you can play. If you want to change FR, you have to change the length of the cavity, because FR is typically C over 2L plus the index. You have to take into account that the light propagates not in vacuum, but in a medium which has an index. But you can play on L. But another parameter on which you can play also is the intensity of the laser, because the intensity will change N, the index, which is responds non-linearly to intensity. So you have two parameters, the length of the cavity and the intensity of the laser. And you have two quantities you want to fix, it's F0 and FR. So with two parameters, you can fix them independently. And that's the way the system is locked. You measure F0 and FR, and you adjust them by changing the length of the cavity and the intensity of the field. And you see here that this is the expression. And you get a phase factor, which is EI omega naught tau. And omega naught is just F0 plus n minus 1 FR over 2. And this quantity is just the average frequency. It's a frequency, you have a square spectrum, and if you take just the average frequency, this is a carrier. This is a frequency that you have inside your envelope. And you see that if you fix F0 to be a multiple of FR, you get a sine X of X signal, which is modulated inside. And this now if F0 is a multiple of 2 pi, this curve is stable. From pulse to pulse, you get always the same time dependence. And you see that, in fact, if you have n very large, n of the order 10 to the 5, you see now that in each pulse, you have just a few oscillations of the electromagnetic field. And this is what how the frequency comb is working. So I will stop at here for 10 minutes, and then I will show you how you can use this, how you can first extend the spectrum so that this frequency comb will work between one frequency and the double frequency in the optical domain, and what you can do with that. So let's stop for 10 minutes.